Okay, let's start. So today we have Avrim as our speaker. Avrim is the Chief Academic Officer at TTIC. I guess we don't need to introduce him. Everyone knows him. So today he's going to tell us about modeling societal phenomenon with learning theory. Let's welcome Avrim.
I always like to use the mic for anything that's after lunch. Okay. So I'm going to talk about here so three vignettes or results that I want to talk about. Maybe I might not get to all three. I'll talk about some of them. The first is on pessimism traps, joined with work with our former REP, Diana, Kavya, and with Alex Colbert at Emory. Second one on classifying agents who can be incentivized to improve, joined with a Yale postdoc, Yudan, Gazia, Donia, Yale postdoc Dravi, and third one on modeling strategic litigation, joined with Melissa, Han, and Lonnie Cohen in Chicago. Okay, so pessimism traps and algorithmic interventions. Okay, so what's the setting here? So what are pessimism traps? So according to Jennifer Morton, so she writes, so this is just the beginning of the abstract of Reed's paper. I'm just going to read it off, and we'll get into what she describes, and then we'll get into a mathematical model. So she says, members of marginalized groups who desire to pursue ambitious ends that might lead them to overcome disadvantage often face evidential situations that do not support the belief they will succeed. And such agents might decide reasonably that their efforts are better expended elsewhere. If an agent has a less risky, though still somewhat valuable alternative, quitting can be a rational way of avoiding the potential cost of failure. However, in reaching this pessimistic conclusion, she adds to the evidence that formed the basis for her pessimism in the first place, not just for herself, but for future agents who will be in a similar position as hers. This is a pessimism trap. So let's just go into her paper a little bit more. She gives an example. So the student in a high-poverty school who decides not to pursue college because the evidence available to her supports the belief that people in her circumstances are unlikely to succeed in that pursuit is falling into a pessimism trap. By not successfully pursuing this course of action, she's not only failing to provide countervailing evidence that people like her can succeed in that pursuit, but she has reinforced the evidential basis for the next student who will reach a similarly pessimistic conclusion. And then she goes on later to contrast her view with some other papers saying that where other papers say, well, just, kind of, you had to do it for the people coming after you. And she says, well, I will argue against the view that such agents have moral reasons to believe against the evidence. Agents who are already in vulnerable positions do not have a moral obligation to take on additional potentially costly risks in order to provide evidence for future agents in similar positions. Okay, so, all right, that paper doesn't have any math in it. So we're going to talk about this. Let's try to get a mathematical model for some model for what's going on. We can see if we can decide ourselves if we think it's a reasonable, for sure, simplification. And then what does that suggest could be done? So there's actually a really nice mathematical framework for situations of this kind called information cascades. Okay, and so what I'm going to do is describe this. It's a classic mathematical model. So I'll describe, if you haven't seen it before, let me describe what an information cascade is. And we can see that it has a nice connection here, and then we can see things we can do about it. Okay, so here's a basic information cascade model. So there are two action choices, A or B. So think of going to college or not going to college. One of them is better for you, and one other is worse. Okay. Let's imagine actually we have a series of agents, and they all have the same better action. So one of these actions is actually globally better, at least for this series of agents, and you're one of them. And the other one is called globally worse. Now, which one's better? Well, let's say each agent I has a private signal. So it's some information that they have. It's a signal, it's just some bit they get about which action is better. And let's imagine these are IID, and they're correct with probability, say, 75%. So you have some, from your experience, you have a belief about which one is probably better. You know you might be wrong, because you don't know what's better or not. But, say 75% chance that the information that you have is correct. Okay? Right? Now, here's the model. The model is that agents see their own signal. They don't see anybody else's, but they do see the choices that previous agents made. Okay? So agent 1 makes a decision, go to college or not. Agent 2 can see what agent 1 did and makes their own decision based on what the previous person did and their own signal. Okay? And we'll imagine that agents rationally make their own choice using Bayes' rule. And their ties are going to happen, and it doesn't really matter how you break them, but it's most interesting actually to break the ties in favor of your own signal. So if it's equally likely based on what the previous person did and what your signal is, you break ties in favor of your own signal.
I guess I'm confused by Bayes' rule. Do they not know what the probability of correctness of the signal is?
Oh, they know. I'll give an example. Hold off until after I've got an example. Okay. Let's say a priori, before seeing the signal, each choice is equally likely to be correct. So so let's go. Here's an example. Person number 1, agent 1 comes along, their signal is B. So agent 1 will choose B. Okay, let's just, why are they choosing B? Well, because their signal was B, but let's just kind of work out. So what is the probability that B is better given their signal over the probability that A is better given their signal? So by Bayes' rule, that's the probability of seeing their signal given that B is better times the prior probability B is better over the probability of seeing the signal given A was better times the prior that A was better. We assume that the priors are equal, so those go away. And then, okay, the probability of seeing your signal given B was better is 3/4. Probably seeing that same signal given that A was actually better was only 1/4. So great, 3/4 over 1/4, 3 times more likely that B was better compared to A, you'll choose B. Okay? Good. All right. Let's look at what does person 2 do. Let's imagine agent 2 comes along, their signal is also B, and they see what the previous person did. So agent 2 will also choose B. If we just kind of work out what are they saying, well, what's the probability B is better given their signal and what the previous person did? Well, the previous person chose B, which means their signal must have been B, because otherwise they would have done A. So now we know the previous person's signal was also B. So we got 2 B's, okay, and so each one's 3 times, okay, so given that, if really B was better, okay, it'd be 3/4 times 3/4. If A was better, it'd be 1/4 times 1/4. So it's actually 9 times more likely B is better. You're going to go with B. Nothing surprising.
And the signals are IID.
The signals are IID. Yep. All right. So now, what if agent 3 comes along and their signal is A? So their signal is A, but they know the previous 2 people did B, which in fact means their signals were B. First person for sure, the second person, if their signal was A, there would have been a tie, which they would have broken in favor of doing A. So this actually means their signal was B. If you break ties the other way, the cascade actually starts earlier. There's a cascade no matter what, but here's where the cascade starts. Why am I saying cascade? Well, what's happening, your signal's A, but these 2 people did B, their signals were B. It's actually more likely B is the right answer, given that they both got a B and you only got an A, so you will ignore your signal and go ahead and do B. Okay, just the probability, if B was better, okay, it would be 3/4 times 3/4 times 1/4, whereas if A was better, it would be 1/4 times 1/4 times 3/4. So again, 3 times more likely B is better than A is better. Okay, so you'll go ahead, ignore your signal and go ahead and do B. That's the best thing rationally for you to do. So notice what's going to happen now, though. We're now stuck. Every agent from now on is going to ignore their signal and do B. And so the whole system is stuck in doing B. Okay, this is called the information cascade, and it seems like a reasonable model, which we will use for a pessimism trap. And okay, it's somewhat unlikely to happen. After all, if A was really the better action, it's somewhat unlikely for the first 2 people to both get B as their signal. That's not crazy unlikely, it's just 2 people. And so, it ends with non-negligible probability.
So, can I just play with it a little bit? So, my initial reaction to it is a paradox. right? Because we should be getting information. And the more information we get, the better our decision should be.
Right.
But I think the resolution is that the information disappears.
We're not getting information anymore.
Right.
We only got information from here. Everybody else's behavior is not giving any new
So there's
information.
no new information.
There's no new information. Right. That's right. Absolutely. So you could tell people, oh, ignore the history, follow your signal to create new information. But that's asking people to do something which is against their interests, and you might argue
That's the moral argument.
that's how it would mathematically describe her argument.
So I want to go back to my question. It's possible that I'm missing, I haven't taught machine learning in a while, but if I have observed the signal, why should I look at history? Isn't the rational thing to do is to say just having a direct information which tells me the 75% probability the signal is correct and I should just do it?
So these are IIDs. So
Why should I use the Bayes rule? I guess that's the question.
Sure. So it's like, there's, so there's a coin which is either more likely to come up heads or more likely to come up tails. You don't know which. You flip it once, you see the outcome of a single flip. You also have other flips you could observe. If you can observe them, you'd like to do that. So that the first two people got a heads, you got a tail. Still more likely it's there's two kinds of coins in the world. Some where this you can think of this as there's a coin that's either 75% biased towards heads or 75% biased towards tails.
I understand that, but isn't what you just showed us argument for not using the Bayes rule?
No, I mean, really is. If you're person 3 and you got an A and the previous people got B, you're better off personally choosing B. I mean, people later on are going to get less information. So, yes.
Maybe this is related, but where does the signal come from?
Oh,
The signal could include information about the history.
yeah, so these are assumed to be IID signals that you imagine that everybody has like their own personal experience and that these are different for different people. So that they're, you're a 10th grader and the person before you was an 11th grader and the person before you was a 12th grader. They're completely different. So they're assumed IID. So and the only way they're sort of related is you can observe the action.
But that's not true of the pessimism trap.
So that is what's happening. So you see the actions other people take, but your signal is just maybe your signal is based on your performance in school or something like that, or some.
So last question for a while. Another unrealistic assumption here is that the same action is better for everyone, which is clearly not true in life.
Yeah. So actually, we'll get back to a model that allows for a world in which there are different actions that are good for different groups of people, which I'll call communities, but community just means a group of people that have the same better action and kind of know who's there. But we'll get back to that. Good. So what I want to do is see if we can use this model to suggest something to do about it. First, here's another way to look at this kind of mathematically, which is you can view this as a random walk or Markov chain of the following type. So we can think of this as an absorbing random walk on the line from -2 to 2, where the current location is the number of A signals that have been revealed by the world so far, minus the number of B signals revealed by the world so far. So we start off so in a world in which A is the better action, we start with 0. 75% chance the very first person is going to see an A, and 25% chance they're going to see a B. But if they do see a B, okay, we get to here. Second person, 75% chance they'll see an A, 25% chance they'll see a B. But once you have 2 Bs, then you're stuck here forever. And more likely you'll get stuck here forever, which is actually the good side, but non-trivial chance you get stuck here forever. It's a 1/10 chance if you work it out, and a 9/10 chance you'll be here for these particular numbers. In a world where B is a better action, it's the exact same Markov chain, but the other way around. Okay, this is what's happening. And so in this view, a pessimism trap is when the unfortunate things happen that we end up there. And that's where things get stuck. Okay, so to talk about interventions, let's add utilities to this. So like I want to add like some value to you of better and worse. So let's just say the better action gives a utility of 1, the worse action gives utility of 0. You still know which one is better and which one is worse. And so now, if you're at -2 and your personal signal is A, if you work it out, your expected utility of choosing action B is 0.75. Your expected utility of action A is 0.25, and that's why you're choosing action B. It's 3 times better than A, just because it's 3 times more likely that B was the right thing, was the better action, given all the information you have. A. On the other hand, if you're at -2 and your signal is B, even more in favor of B, your expected utility of B is 90.96, and of A is 0.4. The probabilities are those. Okay, fine. So now that we've converted everything to money, or at least utilities, let's say utility is the same as money. One thing you imagine doing is intervening by paying people to do the action that, we think is best, like action A, like giving a scholarship for doing action A. Scholarship for going to college. So what would happen? So here's, you work out. If the scholarship is less than 0.5, it's not going to be enough to help. They're still going to be stuck there because less than 0.5 is not enough to raise the expected utility of A above utility of B. Okay, great. If we pay more than 0.92, then it will actually get agents to choose A regardless of their signal. So people will go to college if you basically, in this view, pay them to do it. Okay, that's good in a way, but no new signals are revealed. So once you stop paying, rational people will go back to choosing B, because they'll go and look at all the people who chose A before them, and they just went to A because you paid them to do it. It says nothing about their signal.
Are you paying them to do the high utility one?
I mean, we're paying them to do A, and let's say that we
Doesn't that
believe.
provide more information about which is the high utility one?
Okay, so good. So I'm imagining that the agents do not kind of ask, why is the government or whatever paying me to do this thing? And they're not saying, oh, because they're paying me to do this, maybe that really is the better thing for me to do because they know something about me that I don't. So I'm not in that world. And later we'll get to a model where you want to subsidize people to do the right thing, but you don't know what the right thing is because the right thing is different for different people. So it's really like that. So I just want to point out, if you subsidize too little, you don't change anything. Subsidize too much, you will change behavior, but the moment you stop, people will go back to what they're doing because you didn't get people to reveal more information. But if you instead subsidize an in-between amount, then the next agent will follow their signal. Okay, so they'll actually, if their signal's A, they'll do A, if their signal's B, they'll do B, and then that'll give information that future people can use. And so in general, if you subsidize by whatever amount is needed to get the next agent to follow their signal, then what you get is you'll get rid of that absorbing part of the markup chain, and you look like this, and now you get to something that's very nice. So things could still go the wrong way for a little while, but with probability 1, this will eventually reach here, and that actually will high probability will do it very quickly because it's a random walk that's biased this way by a constant fraction, so it's going to get here quite fast. You're only trying to get to +2. Good. So that's kind of nice. And so the kind of summary here is by giving just enough subsidy to cause agents to rationally follow their signal, you could break this pessimism trap without asking agents to sort of do something that's not in their best interest. Of course, we have to pay them, but temporarily. Once it gets into above, the -2, then you'll have to. Okay. So now let's make it more interesting. Let's imagine that there are multiple communities, subgroups, where the correct answer might be different for different subgroups. So what we're going to assume here is the individuals in each subgroup, they only pay attention to those who've gone before them in their own subgroup, in their own community. So they know who's in their community, they know the best action is that for the same for all of them, but there's different communities sitting around. Okay, that's not exactly realistic, but it's at least better. Imagine that we, as some sort of overall agency, first of all, 2 things. Imagine that we are not allowed to discriminate. We can't give a subsidy to one community and not another. Imagine also, we don't even know what's best for each community. Maybe some of them A is better, some of them B is better. fact, we don't even know who's in what community. We don't even, these are just subsets that exist and we don't even know. We don't know who's in which one, we don't know their current states, we don't know what's best for each community. Can we do anything? So it turns out we can still make this work by choosing a random subsidy at each time step from an appropriate distribution, either in favor of A or B. So we might subsidize A. Maybe like A is go to college, B is go to trade school. Sometimes you do A, sometimes you do B. Okay, I am going to assume that our time scale is such that people aren't going to just wait around for a sale. It's not like, oh, okay, maybe tomorrow there'll be a big, just check the web page, refresh it every day until I get a lot of money. Because imagine it's a time scale changing things year by year or something like that, so that it's, you have to make your decision. Why? Okay, so here's a nice property of subsidies in this model. For any given community, at any given time, there's going to exist values, subsidy values, A greater than B, where think of a negative numbers as subsidies for B and positive numbers as subsidies for A. Okay, so you can subsidize each one. With the following property. If the subsidy is greater than A, then agents will choose A regardless of what their signal is. If the subsidy is less than B, so maybe it's negative, more negative than B, agents will choose action B regardless of their signal. And in between, they'll follow their signal. Okay, that's what's going to happen. In particular, there's no fourth thing. There's no subsidy that will cause agents with signal A to do B and agents with signal B to do A. There's no way to get people to do the opposite of their signal. They'll either do something that's just because you paid them, or they will follow their signal. That's the only, right. So what that means is that at each step, either the current agent takes a step in their community's random walk, or they don't. They don't if their action is kind of not revealing, or it is revealing, in which case it's a step in exactly their walk. And so, so that's the only thing that happens. So basically all we're doing is we have these walks that are kind of stuck, and every time we have a subsidy, there's some chance that that next agent will actually take a step. And as long as we can get these walks to take steps, they'll all go in the right way because they're all biased. Okay, so we just need a probability distribution so that for each community that's stuck, there's a reasonable chance the subsidy is between B and A. So, okay, so that's kind of this summary. And so kind of, okay, so with this sort of, kind of like here, so we propose information cascades as a simple mathematical model to try to model this phenomena of pessimism traps. Just just modeling some aspect of it, but I think it's clearly not realistic, but it's I think it gets at some of the things that are described as going on. I'd suggest information revealing subsidies as a way of helping break out of these traps without asking agents to not act rationally or withholding information from them. So there's also been work on kind of if you have a world where people can't see what everyone before has done, but they can only see a little bit, then maybe these won't happen. But that's a little bit like just not showing them information. Okay, maybe. And just the last thing is that what's kind of nice is that at least in this model you can do this even if you, the subsidizer, don't know the current state or best action or membership.
Just to confirm, so if everybody assumes that they're different from everybody else, which sounds reasonable to me, but whatever, then the subcommunity size is 1, and that 0 subsidies brings us back to just looking at your signal, ignoring everybody else, correct?
That's right. If everyone is,
Individualistic.
if it's just individualistic, people will just look at their signals and this thing never happens. That's right.
So I wonder, besides subsidize, can you kind of selectively, basically promote the positive case? Because typically when there were good example, like we saw them on the news, and that I wonder whether that's going to affect the belief of the agent actually happy to shift it towards the positive side of it.
I mean, it's so let's see. I guess I'm not sure how to model that. It can certainly, certainly kind of things that people have talked about. Information cascades are like rather than having a complete graph where everyone sees all the actions, you have some sparse graph where you just see a small random subset of the past ones, and then you'll have a lot more independence. But that's a little bit like hiding information. I guess you're saying like to promote, show information or show things. It's possible one could have a model for that. What I like here is that there's no, this setting doesn't require that people believe that the subsidizer or government, whatever, like knows what's right for them. So they are acting, you know, kind of rationally in a world that's just, okay, they're providing money for this, that's all. But yeah, there's certainly other possible. Okay. Okay, so now I want to switch to something completely different. Some work on a learning model where agents have the ability to improve. This is with Don because you told me how to drop you. So here's the setting. He's not here. Oh well. So imagine that you have a test that's an excellent predictor of whether someone will be good, will be successful in some task, like whether they will be a good employee, safely drive a truck, or do well in intro to machinery. Okay? So in particular, you imagine that there is some threshold, theta, so that those who perform better than theta on your test will do well in, say, intro to machine learning, and those that score below theta will not. Okay, this is not exactly realistic, but you know, maybe there's some test you have that, you know, in order for students to take the class, they have to take this test, and there's some threshold where those who perform better will do well, and those who score below that. If you don't know the exact value of theta, but you have past data on who did well, who didn't, then this is a, you know, it's a simple learning problem in one dimension. You have some positive examples and some negative examples. And then you might, you know, pick some threshold in between the smallest positive and largest negative. Maybe you pick the halfway point as your data. Actually, as an instructor, I don't know if you do that. I don't know. Greg, if you saw, you know, people doing well in intro to machine learning and people who did poorly, would you want to pick a threshold halfway between? Maybe.
I don't think of it in binary.
Maybe a realistic person. Okay, so go back to that. Now let's imagine that people can put in effort to improve. They can study for the test. They can practice, increasing their score by some amount. Maybe people, you know, if they really have no background, they can't like do arbitrarily well. But I mean, maybe there's different amounts they can improve for each person. But it's possible to study and, you know, learn. That's the whole point of courses. And so, you know, they can study in advance to do well on the test. So it could be different for each person. So delta will be the amount that someone can improve. Actually, in general, it will be a higher dimension. But think of it in one dimension. Delta is the amount you can improve. Maybe delta x is different. Okay, so suppose we're in that kind of world. So there's two things. One is, on the one hand, there's actually a big danger if you put your cutoff too low. Okay, so imagine if your cutoff is below the actual true value needed, then, you know, to do well in the class, then people will study up to passing the test, which might not be good enough. So they might, you know, if they're not qualified, they'll study to be able to pass your test, but then they still won't do it because you do. On the other hand, there's a nice benefit of putting your cutoff safely a little higher. Let's say at the smallest positive example, which in this world is guaranteed to not make any mistakes of this kind, because we're assuming there really is a threshold somewhere. Which is that if the gap to the true theta is smaller than the delta people can improve, you can actually hope to get zero error. Zero error in the following sense. A, you never have a false positive. Everyone you admit is actually qualified. And B, any actual positive, like anyone here that would normally be an error, can put in effort and pass your test. And so there shouldn't be false negatives as long as, you know, they'll just have to put in effort. So there's a trade-off here that we've gotten rid of errors by forcing people to do work. But okay, that they're improving themselves, you know. So that's kind of, okay, so this is going to be the model we'll look at, is a model where agents want to be classified positive. They can put an effort to do that. And so there's a potential to do something that you can't normally do, which is actually get zero error, as long as, you know, by, for instance, in this case, safely putting your threshold higher than the correct value, but maybe it's not too much higher, so that everybody in the error region can actually improve to your value, then you won't make any mistakes. Now, maybe you made the threshold higher than you had to, but that's okay. All right, so that's the same. There is, of course, the danger if you put it too low, then your error might actually be higher than it would have been otherwise, because all these people are improving up to your threshold and creating errors you wouldn't have. Okay, so that's the model that we studied. It's kind of interesting because usually in pack learning, you can never hope to get zero error from a finite sample unless the whole setting was like really trivial. So, yeah, usually in any non-trivial setting, you can't really hope to get zero error. But here you can. But you are forcing agents to do it. Okay, so this is a model for pack learning under improvements. We assume it's a target function from some family. It might be over a multidimensional space. Each agent has some region that they can or would be willing to improve to be classified as positive. We assume the classifier is made public, so you can think of it a little bit like allowing someone multiple tries. And if it classifies you as 0, but there's some point in your improvement set that you can reach that you get classified as 1, then you will move to some such point. And we imagine that agents will break ties adversarially or arbitrarily for us. So, which roughly corresponds to if agents can improve to get classified positive without actually making themselves really positive, they will prefer that to so anyway, we'll just assume they break ties. Okay, so some theoretical results and some semi-synthetic experiments. So theoretical results, so you can have classes of infinite VC dimension that become easy to learn. Like the simplest version of this is if people can improve arbitrarily, then all you need to do is, well, if you haven't seen any positive examples in your training set, just say everything's negative. But if you've seen one, just say, be like that person. All right, just find a positive example, say, be like that person. And if everybody can, and everyone was trying to be like that person, people can move arbitrarily, then they'll do that. Great. You can also go the other way around. You can have classes of small VC dimensions that become hard to learn, especially with adversarial tie breaking. You get nice sample bounds for achieving 0 error with high probability in some interesting cases. I'm not going to go into too much in this. But in general, the theory favors classifiers that only predict positive when they're sure. And the main reason is that the sort of false positive, so yeah, predicting positive on regions that are actually negative has this double whammy that not only is there a region of points you're making a mistake on, but you might have all sorts of points moving there, creating even more mistakes. So it's even more dangerous to predict positive when you're not sure, but less dangerous to pull in a little bit because the agent will be able to move. So in general, in a setting, let's say a linear classifier, rather than doing something like an SVM, it favors doing something like this, which is what you would do if you say, any linear classifier has to classify this is the positive region, must classify these guys as, these guys have to be positive if they're really, if the data is linearly separable, but these regions could be negative, so you'll just say negative. You only say positive. And so it favors classifiers. And then some semi-synthetic experimental results. So semi-synthetic. So just take some real data, choose some features as being modifiable up to some amount. So we're imagining delta in these experiments as an L-infinity ball in some subspace, or some features that agents can modify, we imagine, others that can't. We'll train some network on training data, and then for each test point, use PGE to simulate agent behavior like an adversarial machine learning. So they're going to use gradients to try to become positive if they're currently classified as negative. Now, one thing that's different here compared to adversarial machine learning is two things. The smaller thing that's different is the agents are just trying to go from negative to positive as opposed to just making mistakes. The bigger one is that we assume that changes are real. And that means we need to know if changing the features would have actually changed the label. Okay, because they're sitting somewhere in space, they're doing something and moving somewhere else. Maybe that actually made them positive. The problem is all we have is data. We don't know if you took this point and modified the features like that, would they have become positive? So we need a proxy for that. So we just create a proxy by simulating. We need to know F star. We don't have it. So we simulate by training a separate classifier of a different type, decision tree in these experiments. There's zero error on the entire data set, training and test. And then using that as if it were reality to evaluate the final thing after they've. Okay, you could imagine doing this different way. Then we can compare classifiers trained with standard loss functions with those trained on some more risk-averse loss functions. For instance, putting higher penalty in false positives and false negatives to cause the classifier to move in a more risk-averse direction. Yeah. And then some graphs and any questions asked Kizia. Kind of things that happen. So going to the right, the agents can improve farther. And so, let's just look at this one. So this line is just if you have equal balance of false positives and false negatives. If you have classifiers that are aiming, they're risk averse, so they're trying to avoid false positives, then if agents can't improve, well, they're doing worse because they're making more mistakes because they just put all this penalty on one kind of mistakes versus the other. But as they're able to improve, then you get down to the near zero error regime. Where you are safely really doing you're only calling positive things you're sure and forcing everybody else to improve to there. And if they're able to, they will. So it's just interesting to kind of look at this. And there's different kind of ways of trying to do that. Encouraging the classifier to be risk averse, and some of them seem to work better.
Isn't this making your model overconfident though? Like there is little room for uncertainty.
I don't know if I would say that. What I would say is that if you're uncertain in a region, this setting favors saying negative if you're not sure, rather than saying what you're most likely to do. So another way to do this would just be to train a regular old classifier, but rather than putting the threshold at 0.5, put the threshold at 0.9. But we just found that didn't work as well in these experiments as in the it worked better in the training process to just change the loss function used in training the network. You could imagine just taking a regularly trained network and just saying, hey, if you're unsure, but we just found it worked better to do it this way. Okay. We were also then kind of looking at something, how sensitive is this to how you choose, how you model the risk score. Okay. So I want to just take a few minutes at the end then to talk about something, again, completely different. So in theory perspective on strategic litigation. So this is some work with Melissa Hahn and Aloy Khan in Chicago. If you thought the first one was unrealistic, this one's okay. Here. So, but we're going to try to model something that, just to get a feel. So, so what is strategic litigation? Okay, so first of all, what is the law? Right. So there's law that's, Congress makes laws, but a lot of law, common law, case law, is based on prior decisions of courts, and it's based on precedent. Courts make decisions, and then new courts decide a new case, a new situation. They decide by looking at how were previous similar cases decided, and then they decide based on that. And then, the Supreme Court decides cases, and they give their reasonings, and the lower courts have to go ahead and see a new case, and they have to see, does this apply, does that apply, use that. Okay, so now sometimes, so we're looking at strategic litigation. So this is the strategic agents who are trying to modify the case law, try to create precedent that favors them. by bringing cases that they believe will be decided in a certain way, creating precedent that will then allow them to do something, disallow other people from doing something. So we want to model questions here, like, well, what cases should they bring? Does it ever make sense to bring a case where you expect the court to rule against you? And how much of an effect can the strategic litigator have? To do this, we're going to take a learning theory perspective that will involve making highly simplistic models of everything. So, here's a learning theory model. We're going to think of a case fact pattern, like who did what, all this stuff, as a point in some feature space. Okay, so there's a plaintiff, defendant, there's all this stuff, all the information is a point in some feature space. That's not too crazy. That's reasonable. So here's a bunch of points. We're going to model the Supreme Court as some binary labeling function that labels some as being, this was in favor of the plaintiff, some in favor of the defendant. Okay, some yes, some no. Now, actually, they don't just give an answer; they also give a text reasoning. Okay, so we're kind of either ignoring that or folding it into the learning outcome. I think handling that better would be, a nice way to make this more realistic. But right now, we're modeling Supreme Court as just sort of deciding in favor of one side or the other. Okay, so they decide in favor of the ones and the blues and against the rest. We're going to model case law, so how lower courts use this precedent to decide new cases. Now, what they use is not just the decisions, but also, the actual things that all the different judges said, the justices said, but we'll just think of them as using the results as some public learning outcome. So basically, some new case is a new point has to somehow be decided. So how do you decide a new case given this? Well, in some way, the lower court has to create a rule based on the previous things to decide whether a new point should be red or blue. And so we can think of that as a learning algorithm. It takes in the past data. It's not like a learning algorithm we're coming up with. It's just modeling the courts as following maybe it's nearest neighbor. What was the most similar past precedent? Maybe it's, find me a linear separate, whatever it is. And it might not be the same as what's in the Supreme Court's head, but some learning algorithm that decides new cases. Just think of it as nearest neighbor. Take a new case, decide based on the most similar previous case. Ignoring the reason. There's reasoning in the Supreme Court's decisions saying that these parts were important and these parts weren't important, so it's not really nearest neighbor, but let's pretend. Maybe it's a SVM. Not nearest neighbor. So. And then we'll model the strategic litigator as an entity who wants the rule produced by this learning algorithm to be close to their own desired function, which might not be the same as the Supreme Court's. And for the moment, let's imagine that the Supreme Court has actually a well-defined function in its head, and that doesn't change. Okay, in the real world, you get new justices, and all of a sudden, green is blue, and up is down, and whatever, and things change, and precedent gets overruled. But let's imagine that F star is fixed. So here's a simple example. Maybe we have instance case in R to D, so case fact patterns are D-dimensional points. F star and G are both linear separators. So G is what the litigator wants. F star is how the Supreme Court is deciding things. There's no existing precedent. So there's F star, that the actual, the Supreme Court says these are allowed, believes these should be allowed and these shouldn't. You would like these to be allowed and those not to be allowed. Okay, so and imagine the strategic litigator can bring up any case it wants. So that's also not realistic because you can't just make up cases, they have to actually exist in the world. And those F star, which is also semi-realistic. And let's imagine that maximum margin classifier, maximum margin separator, or nearest neighbor is the public learning algorithm. Well, in that case, not hard to see, the strategic litigator can achieve any G whose normal vector has angle less than 90 degrees to the true F star by just bringing two cases where the nearest neighbor classifier would do according to G. So you bring something a little down here, a little up there, and that'll cause the thing that you want rather than this. Right? So this is just a simple example where you can't create things that are more than 90 degrees. It's not too hard to see, but you can create anything less than 90 degrees with two cases appropriately separated. Because this is an example of a way that you could then get the courts to produce this other. If the precedent exists, then this problem becomes harder. There's some optimization. Here's another example. Imagine case fact patterns, I guess what these are called, are points on the line. So it's one-dimensional things. We have arbitrary functions, so there's things that go up and down. And there might be existing precedent, and the public algorithm is nearest neighbor. So for instance, imagine there's existing precedent here, which is this is allowed and this is not allowed, and then halfway between is here, and this F is the current rule the lower courts are using is, okay, if you're to the right of the middle point, that's what's allowed, to the left is what's not allowed. F is going to be what currently the courts are using. Imagine what's in the Supreme Court's head is F star, and the reason F is different from F star is just because this is the halfway point between the data we see. The cases that have been brought to the Supreme Court, there haven't been cases brought to the Supreme Court near here yet. But maybe you would like the thing moved more to the right. Okay, that's what you would like. So then you would want to bring a point, here, something that the Supreme Court will say no to, okay, but then it'll kind of move, now these guys are closer to the no, and then that'll get you your G. Right? That's the kind of thing. In general, given some case budget and some possible cases you could bring, and given knowledge of F star, you could have run a little DAG programming algorithm to solve for the best K cases to bring, so that what you get is as close as possible to the GU. Okay, but here's some sort of interesting observations. So one, if you choose cases myopic, because I'm not sure what, so we're acting as algorithms for the strategic litigator. Okay, not sure morally you want to do that, but okay. Well, let's see. Okay, so if you choose cases myopically, you could create unnecessary, unrecoverable error. So here's an F star, here's a G. Currently there's no data. Let's imagine the current F is all negative if there's no data. Myopically, all the positive cases are equally good. They will change F from everything's negative to everything's positive. But you don't want to, if you don't choose your case far enough to the right, you won't be able to get the transition where you want it. You need to choose far enough to the right so you can kind of get that G transition halfway between. You might need to bring a case you disagree with. So imagine that you would like the exact opposite of the Supreme Court's rule. The Supreme Court says everything should be disallowed except for this little thing here. You say, no, you'd like everything to be allowed except for that little thing. Well, again, if we start off, let's say everything is negative until you see any data, then you would want to bring a point that's allowed. Say, well, nothing's allowed, right? You agree that things that are allowed here, and the Supreme Court says, yeah, things are allowed here. Even if you personally disagree with that, that will at least produce a rule where everything's allowed, which is closer to what you wanted than the current state. And you may need to make things worse before you can make things better. So another example is something like this, or F star G or like that. You can sort of work through the cases. There's no way to have the rule monotonically approach what you want. Eventually you will, because you agree with the Supreme Court, but you might have to get farther before you can get back. So you can have situations. So we have a little model for what if the current Supreme Court disagrees with existing precedent. For instance, maybe existing precedent looks like this, but a new court arrives and says, sorry, this whatever thing, there used to be a detailed rule for when a certain thing was allowed or not allowed, and now the Supreme Court feels that no, this should never be allowed. And maybe you as a litigator, okay, so we're imagining a litigator who actually is in favor of the Supreme Court, but we'll model the court as not gratuitously throwing out precedent, which they're supposed to not gratuitously throw out precedent, but which means if a new case can be decided without throwing out precedent, so there's some function in the family consistent with the new thing that they won't throw it out. So here or something, and then fine, it's still possible, you can still have a rule. So they won't actually throw it out, but if you give the point over here, now all of a sudden they'll say, well, this is negative, and now you have to throw out some precedent because it's not consistent anymore, and so that will actually cost something. So you could have a model like that. They'll throw out then some minimal substantive precedent. So that turns out to be an interesting model, and you can sort of analyze the problem and how points might select cases in that case. Right. In that case, the strategic litigator would want to bring some cases that sort of force all the positives to get thrown out. All right. Anyway, so then a few other results. So in learning theory, this is closely connected to the notion of teaching. So it's something called teaching dimension that's been around for quite a while, which is the size of the smallest data set whose labels uniquely determine F star within a family. So it's a set of points that the only way to label these points in this way is to use the right thing. So you can think of it as, if you have someone wrote a program, what is the sort of smallest set of test cases? So that if you get those test cases correctly, you must be the correct program as long as you are within this family page. So that's a classic notion. And a little more recently, notions of teaching dimension for a given learning algorithm like SVM. So this is very much like, so what we're looking at is actually very much like this, in this case where G and F star are the same. So then you're asking, what is the fewest cases you need to bring to cause this learning algorithm to learn the right answer? But we would like it to learn the wrong answer, or our answer. So that in that sense, we want to know not just how many, but can we cause it to learn our G rather than the actual F star or something else? Which G can you get it to learn, or how close can you get it? It's also very similar to clean label data poisoning attacks in adversarial machine learning, which is sort of actually got us thinking about this first when we start talking about Maloney, which is in clean label data poisoning attacks, an attacker adds correctly labeled points to an existing data set so that usually for the goal of having the learned function be wrong on some particular point. The attacker is trying to cause you to make a particular mistake, but is doing it through adding incorrectly labeled points. Whereas what we're asking is the same kind of model. The labeling function is still the same part, it's just which points it's labeling is all you can control. But the goal isn't to cause a particular a mistake on some point. The goal is to cause the overall law to move towards something that you want. Okay, so that's just okay, so that's it. And
So we have time for a few questions. Questions?
Is there anything the court can do to prevent this to some extent?
Well, I mean, in the real world, it's a question whether the court wants to.
Is there a
So there is a notion of standing. Like you can't, you shouldn't. You can only bring cases that you have. Just because some law bothers you, you can't bring a case. You have to actually show harm, right? So the litigants have to at least find somebody who was harmed, and or at least claim that there was some harm. So, for example, and then that's often something like I just saw it. I was listening to the news this morning, and I guess Florida is suing Target for their DEI policies, saying that, oh, well, because Florida's investment funds includes money in Target stock, and that their DEI policies are hurting Target stock, and that gives them, okay, so the court might just throw that out and say that's great, or the court might be on their side and say, oh yeah, that's sure. So there's certainly things that the court can do if they just think that formally, you're not supposed to, you can't bring a case that's not actually hurting you. All right, so that's
I think also in real world, the Supreme Court cases and to some degree federal cases in general, they often are very careful at indicating where the boundary is. They say, we'll decide it this way, but it is very close to the boundary, and if only these things were different, we would not say that. So, because those are not binary flags, but sometimes 100 pages of opinion.
Right. So I think maybe a more realistic model here is one where, in addition to labeling, there's some other information. There's a whole bunch of text, and that is going out, and there's some public function takes in the text somehow. Yeah, so I think that would be a better model for sure.
Is it possible to understand the influence of the actual algorithm they're using? Because one way to interpret what you just said would be just, the code is actually using a very difficult, it's not nearest neighbor, it's not SVR, it's probably something very complicated. It still uses the input data, but it is some arbitrary true labeling, not the true labeling function, the labeling function that the code uses. So then you can maybe say, if you use these kind of nearest neighbor or SVM, and you can even get a situation where you get the complete opposite of the Supreme Court, but then these other algorithms are more robust to this.
Right. I mean, I guess you want to think of the algorithm as something that's implemented by a court and is understandable to people, because in some sense it's reasoning. So maybe rather than the nearest neighbor, some form of k-nearest neighbor, saying, look, yes, there's this case that's similar, but look at these other ones that were also dissimilar in other ways. Or think of it as like maybe nearest neighbor where you're arguing about certain coordinates, certain directions as being important. Sure, this is similar in this way, but that's not important. This similarity is what's important, right? The fact that people were the same height is not important. But the fact that they were using whatever it is, that's right. So you can imagine that sort of thing. And then where the cases themselves, maybe the label, in addition to the label, there's some text telling you some information about which aspects were important. I think that could be a nice intermediate model between just a full text arbitrary function. Well, yeah, the text says that these features were important in that decision. Yeah, so but it should still be something simple, because in the end it's going to be people who are looking at this. But certainly, I think maybe a more realistic version would be something where people are arguing about. Think that the similarity in that direction is just not important. The similarity in this direction is what's really.
Could you model the text? Someone brings a case to the Supreme Court. The Supreme Court makes a decision in that case. Instead of saying that there's text, you could say, well, they give a list of other cases that would have been decided in certain ways. They not only decide this case, they publish a set of cases and how they would have been decided.
I'm not sure that would be more realistic, though. I don't know. I guess because they very explicitly, they very explicitly say they will not decide hypotheticals. So they're very reluctant to say, had it been like this, we would have decided something. You almost never see that. It just happens to be the way they do it. It's more like they do tell you that they say there's some rule that they're using, but it's not. Is it a rule that actually applies? It's like what does it mean? Okay, I don't. Anyway, that's my mind. All right, so we're at time.